question is about the sodium vapor lamp, which emits light when its atoms are excited by electrons. We are giving you three quantities, H, C, and E. What do each of the quantities H, C, and E represent? H is a Planck's constant. C is the speed of light in vacuum. E is the elementary charge, which is the magnitude of the electron charge.
Number 2. The diagram shows some of the lines in the emission spectrum of the sodium lamp. 2.1. The yellow doublet of wavelengths in vacuum lambda 1 and lambda 2 is more intense than the other lines. 2.1.1. To what range, visible infrared or ultraviolet, does each of the other lines of the spectrum belong? We will consider the wavelengths of visible light in vacuum to lie between 400 and 700 nanometers. Let's start with the line of wavelength 330.3 nanometers. Since it is less than 400 nanometers, it belongs to the ultraviolet domain. The lines with wavelengths 568.8 and 615.4 nanometers lie between 400 and 700 nanometers, so they belong to the visible domain, whereas 819.5 and 1138.2 nanometers are greater than 700 nanometers, so they belong to the infrared domain.
2.1.2. The sodium vapor lamps are characterized by the emission of yellow light. Why? Because this yellow light is much more intense than the others. 2.2. Is the visible light emitted by the sodium lamp monochromatic or polychromatic? Justify your answer. It is polychromatic because it is made of several radiations with different frequencies.
Part 3. Consider the diagram of the energy levels of the sodium atom in the adjacent figure. 3.1.1. Specify an indicator that justifies the discontinuity of the emission spectrum of the sodium vapor lamp. As we see in the previous slide, the diagram shows discontinuous lines. Observe the adjacent diagram. The minimum energy of the sodium atom is minus 5.14 electron volts, followed by minus 3.03, minus 1.93, minus 1.51, and so on. This means that most energy values do not exist within the energy levels of this atom. Each line in the emission spectrum corresponds to a transition between two energy levels. Since there are missing energy values, there are also missing lines in the emission spectrum. Therefore, the discontinuity of the emission spectrum is due to the discrete energy levels of the sodium atom.
3.1.2. Verify that the emission of the line of wavelength lambda 1 corresponds to the downward transition from the energy level E2 to the ground state. Let's start by calculating the energy of the photon whose wavelength is lambda 1. So we use the formula hc over lambda 1. Replace hc and lambda 1 by their values. Remember, lambda 1 is expressed in nanometers, so we should convert nanometers into meters by multiplying by 10 to the power minus 9. After finding the energy of the photon, let's calculate this energy in electron volts. This is done by dividing the photon energy by 1.60 times 10 to the power minus 19. Now let's calculate the difference of energy between E1 and E2. This gives you 2.11 electron volts. Compare the two answers. The photon energy is equal to E2 minus E1. Then, yes, the line of wavelength lambda 1 corresponds to the downward transition from the energy level E2 to the ground state.
3.2. In fact, the energy level E2 is double.
it is constituted of two energy levels that are very close to each other. Assume that the lower energy level is A and the higher one is B. Draw a diagram that shows the preceding downward transition as well as the downward transition corresponding to the emission of the radiation of wavelength lambda 2. The diagram shows the transitions from both A and B to the ground state. One of these transitions corresponds to lambda 1 and the other to lambda 2. The energy of a photon is given by hc over lambda. Since lambda 1 is less than lambda 2, the energy of photon 1 is greater than that of photon 2. Therefore, the transition from B to the ground state corresponds to lambda 1, and the transition from A to the ground state corresponds to lambda 2.
4. The sodium atom being in the ground state is hit successively by electrons A and B of respective kinetic energies 1.01 electron volts and 3.03 electron volts. Determine the electron that can interact with the sodium atom. For electron A, we will use this formula, KEA equals EH minus EL. Note that EH represents the atom's final energy level if it absorbs all the electrons' energy, while EL is just the energy of the atom in the ground state. Replace EH, KEA, and E1 by their values. You get minus 4.13 electron volts. Now examine the values of E1, E2, and E3. Since EH is less than E2, the electron does not interact with the atom. Let's move to electron B. We will use the same formula. So EH equals minus 2.11 electron volts. Again, look at E1, E2, and E3. EH is greater than E2 and less than E3, which means that electron B can interact with the atom. Why? This will be explained in the next slide.
4.2. Specify the state of the sodium atom after each impact. In the case of electron A, since this electron does not interact with the atom remains in the ground state. In the case of electron B, since EH lies between E2 and E3, there are two possibilities. The atom may remain in the ground state or may be excited to the first excited state E2. 4.3. Deduce after impact the kinetic energy of the electron that interacts with the sodium atom. Electron B interacts with the sodium atom. We know that the kinetic energy of the electron after the impact is given by the kinetic energy of the electron before the impact minus EH minus EL. But EH is E2, which is minus 3.03, and EL is E1, which is minus 5.14 eV. Now replace KE before by 3.03, E2 and E1 by their values. We get the kinetic energy of the electron after the impact equals 0.92 electron volts.